We have a wire of length 10 meters, which is clamped between two walls, and its temperature right now is 30 degrees Celsius. We increase the temperature from 30 to 130, and the question is, in doing so, what's the thermal stress generated inside the wire? We've been given the linear expansion coefficient and the Young's modulus. Alright, this term called as thermal stress is very new to us. So the goal of this video is to understand exactly what this thing means, and we'll do that by solving this numerical. Alright, let's do it. So we have a wire of length 10 meters and its temperature is increasing. And when the temperature of something increases, it tends to expand. When you heat things, they expand. The only problem that we have here is that there are these walls. They are not going to allow this wire to expand. So what's going to happen? Well, this is new for us. We have not talked about things like this before. So what we'll do first is we'll forget about the wall for now. Let's forget about that. And let's just do what we're familiar with. We are familiar with calculating changes in the length when the temperature changes, right? And we can do that by knowing this number, alpha L, the linear expansion coefficient. The number just tells us that if we had 1 meter long wire, and if we increase the temperature by 1 degree Celsius, then the wire would expand. If it was free, the wire would expand by 20 times 10 to the power minus 6 meters. That's given to us. So let's first calculate how much this wire expands if there was no wall. Well, it would be a great idea to pause the video because we have talked about this before. So pause the video and see if you can try this on your own. And if you feel like you require more clarity, it would be great to watch that video first and then come back and try this yourself. Alright, so pause the video, try it. Okay, let's do it. The first thing we'll do is we'll build a relationship between changes in the length and changes in the temperature. Very quickly, let's do that. The change in the length, we already know it's alpha L, provided we have 1 meter long wire and we increase temperature by 1 degree Celsius. But if we have, say, 2 meter long wire, it would be twice. For L meter long wire, it would be L times more. So this would be the change for 1 degree Celsius. 1 degree Celsius rise. What if you have 2 degrees Celsius rise? Well, it'll be twice of this. What if you have delta T degrees Celsius rise? Ooh, it'll be delta T times this. Alright, so here is the expression. And now we can just plug in these numbers. We know what alpha L is. We know what L is. We also know what delta T is, right? We can calculate that. Delta T is the change in the temperature. We can just plug in and figure out the change in the length if the wire was free to expand. Let's just do that first. So in that case, we would get delta L equal to alpha L, that's 20 times 10 to the power minus 6 degrees Celsius inverse, times 10 meters times delta T. What is delta T? Well, change in temperature. And that change in temperature is 130 minus 30, which is 100 degrees Celsius. So this is 100 degrees Celsius. Let's just go ahead and do the math. We have 20 times, let's see, we have 1,000 and we have 10 power minus 6. When you multiply, you get 10 power minus 3. The degree Celsius inverse and the degree Celsius cancels. That's good because we want the change in length to be in meters. So we get so many meters. That's about 20 millimeters. 20 millimeters. So what we understand from this is that at 130 degrees Celsius, the wire would be a little bit longer. It would be 20 millimeters longer. This would be 20 millimeters. Alright, now let's come back to our problem. In our problem, we've been given that there is a wall. So, what's going to happen? Well, the wall is not going to allow the wire to expand. So because of that wall, even at 130 degrees Celsius, the length of the wire would still be 10 meters. So by not allowing the wire to expand to its necessary length, it's as if the walls are compressing the wire. You get that? Let's write that down. So the effect of the wall can be thought of as at 130 degrees Celsius, the wire should have had 20 millimeter longer length, but it doesn't. And the reason it doesn't is that the walls are pushing from the sides and making sure that it doesn't expand. In other words, the wire is being compressed. The wire is compressed by 20 millimeters. And now comes the question, what's the effect of that? So what happens when you compress a wire by some amount? Well, for that, let's think of a spring. Let's make a little bit space over here. All right. So here is the original wire, which has been compressed by 20 millimeters, and we're comparing it to a spring. What would happen if you were to compress the spring by some amount? What would happen? Well, then we all know that the spring snaps back, or at least it tries to snap back. And it does so by generating what we call as the restoring force. So there is a restoring force that gets generated over here. Let's call that as F. And you may have already learned that this restoring force is proportional to the amount of compression that we provide over here. Let's call that compression as delta X, amount of compression. And the proportionality can be written as equal to some constant K, and we call this as the spring constant. And a small detail is that since the force and the compressions are in the opposite direction, we would have a minus sign over here. This is Hooke's law. But let's not worry about the direction. Let's just work with the magnitude over here. Now, something very similar is going to happen over here. When this wire gets compressed, it tries to restore itself. And it does so by generating a restoring force within the wire. But we don't exactly talk about the restoring force here, but instead we talk about a quantity called as restoring force per unit area. And when we say unit area, I mean a cross-sectional area. So if you were to zoom in, you can think of this wire as some kind of a cylinder. And so it has some cross-sectional area. And so if you take the restoring force, divide by the cross-sectional area, that's what's important for us. And that quantity is what we call as stress. That quantity is stress. So stress is very closely related to the restoring force in a spring. All right. And just like how over here, this restoring force is proportional to the amount of compression, it turns out that the stress is proportional to the amount of compression per unit length. And we call that quantity as strain. We call that quantity as strain. And it turns out that even these are proportional to each other, or equal to some constant, and that constant is Young's modulus. All right. So stress is force per area. That's what stress is. And strain is the change in length, or the amount of compression per unit length. Per unit length. And Young's modulus is just a constant for a given material. Now, we have actually discussed about this is another chapter called solids. And so if you require more clarity on this, then it'll be better to watch that video first and then come back over here. But anyways, all we need to do now is calculate this stress. This stress is called as the thermal stress. And the reason it's called thermal is because, I mean, think about it. The stress was generated because of thermal expansion. If there was no thermal expansion, the wire wouldn't have expanded or wouldn't have tried to expand, and this strain wouldn't have been developed in the first place. So all we need to do is calculate this thermal stress. Well, let's see what we know. We already know what Y is. That's the Young's modulus. We know delta L. That's 20 millimeters. We also know the initial length L, 10 millimeters. So we can just go ahead, plug in, and calculate what the thermal stress is. So let's just do that. Let me make more space over here. All right, so if we plug in, we get 80 gigapascals times strain delta L. Delta L is 20 millimeters divided by the original length, which is 10 meters. 10 meters. So that gives us, let's see, this 10 cancels, and you have a meter canceling. And so what left is 80 times 2, that's 160. 160 gigapascals times 10 to the power minus 3. Now, giga is 10 to the power 9 times 10 to the power minus 3 is 10 to the power 6. And 6 can be written as mega. So we could say 160 megapascals. 160 megapascals. So that is the amount of a thermal stress generated in this scenario. Now, the effect of the thermal stress can be seen in this picture. So notice over here, due to the thermal stress, the railway track has buckled. Now you may be wondering, well, where is the wall to restrict the expansion over here? Well, what may have happened is that only this part of the railway track may have gotten heated up a lot, and so it tried to expand a lot more compared to the other parts. And so in such case, the other parts sort of act like a wall, sort of like, do not allow the expansion so much, causing this thermal stress, which has made the buckling effect over here. And if the material is brittle, then this buckling can even break the material. So suppose you had a glass rod over here, and then suppose you were to rapidly heat up one small portion of the glass rod, then again that portion would try to expand a lot more compared to the other sides, other section, and again that could cause the whole thing not to buckle this time, but just to break. And this can also happen when you try to cool something very quickly. If you are to cool a small portion of the glass, then that portion would try to shrink, contract very quickly, and that could again break the whole material. This rapid cooling or rapid heating could break stuff like glasses, and we call such phenomena as a thermal shock. And so we need to be careful about things like this when we're dealing with very hot stuff, like say hot liquids, and we're pouring it in, say, things like glass or other ceramic containers.